Welcome back to the Drawing Board by TBPi, where today we'll be talking about exact equations. Are these a type of equation that is an ODE? And to that I would say exactly. So we're going to be looking at why these equations are unique and how you can solve them, and then running through a few examples to see those methods in action. So first we need to clarify, what is an exact equation? Well, if we're just looking at the form of an exact equation, the name comes from the fact that it's an exact, or that it's an inexact differential, and you can look at all the complex things, but when it comes to just two dimensions with just x and y, you can say that you have some function m and some function n, and you'll have m dx plus n dy, and those will add up to 0, making a homogeneous ODE. So both of these functions, m and n, can be functions of x and y. So you could also rearrange this and say something like m plus n dy dx. And this would also be the same thing. All that's been done is you multiply all the terms by dx. So right here we have the actual form of an exact equation. So in addition to the actual form of the equation, we also need to prove that it's exact using a couple facts. So the first of these two facts we have about an exact equation is that the partial derivative of some function f with respect to x, that will be equal to our first function m. And our second fact is really similar. It's that we have some function f where the partial of it with respect to y this time, this will be equal to n. So with those two facts, we can combine those and write them in that form of an exact equation. So we'll have, instead of m, we have partial f with respect to x dx, and then we'll add our partial f with respect to y dy, and those will add up to 0. So this would be the form of the exact equation, but in order to prove that facts 1 and 2 are true, we need to show that something else is true. So what we have to show is that the partial with respect to y of that function m, we have to show that that is equal to the partial with respect to x of our function n. So if this equation is true, we know that facts 1 and 2 are also true, and that we'll have this equation f. So the reason why this way of showing that partial m with respect to y is equal to partial n with respect to x is pretty simple. All we have to do is expand it out. So if we now have the partial with respect to y and partial with respect to x, we can substitute in what we just wrote up here. So instead of m, we can write out partial f with respect to x, and instead of n, we can write out partial f with respect to y. And now just looking at these two sides of the equation, we can see that that is true. We have a partial f on top, then partial x on the bottom, and then also partial y. So showing that this is true for an equation proves, if it's in this form, that it is an exact equation. So now that we know how to find if an equation is exact, how do we actually find that function f of x and y that is the solution for that exact equation? Well, we go back to the two facts we just talked about. So starting with that first fact, which is that the partial of f with respect to x is equal to m, what we can do is integrate both sides of that. And so writing that out, we have that left-hand side now integrated with respect to x is now just our function f, and then the right-hand side is the integral of m with respect to x. Except there's one thing missing here, which is the fact that we took a partial derivative here and just did a normal integral here. So if you remember from just a lot of normal two-dimensional integrals, you would often have a plus c. But in this case, instead of having a plus c, we actually have plus a function, which we'll call h of y. Because if we differentiated that with respect to x, much like a constant, it would just go away to 0. So we have to consider that we have some function h of y. And we can also rewrite this where we just have the integral of m with respect to x is just a function g of x. So the fact that f is equal to a g of x here and an h of y comes from that first fact. So now we can look at our second fact, which we'll write a little bit differently. So we can say that function n is equal to the partial f with respect to y. And now what we can do is expand that out and say that the partial with respect to y of our function f is going to be equal to n. Now, instead of just writing out an f again, we can pull what we just wrote up here for f. So now that we have that written out, we can continue writing out what that actually means. So first, we can just write that it's the partial with respect to y of that function, g of x. And then we could write the partial with respect to y of h of y, but since it's a function of y, we could also just write out that it's h prime of y. So now we can rearrange this a little better and find what that function h of y is. And so we'll pull everything to one side and then integrate it. So here we can see we have h of y, and that ends up being the integral of our function n minus partial with respect to y of our g of x, all of that integrated with respect to y. And we can plug this in even further, and remembering that our g of x is our integral of m dx, we can combine this equation here with what we wrote up here for a function of f. So here we have all of that written out. Our function, which is our solution to our exact equation, is the integral of m dx plus the integral of, with respect to y, of n minus the partial with respect to y of that integral of m dx. So there's how we find the function. And the other thing we know about this is that it's actually equal to c, some constant. And you could also see in some cases where that's instead of 0, but it ends up being the same thing because you're going to have some constants when you do these indefinite integrals. But either way you look at it, all you have to do is go back. If your equation is in this exact form, you can prove that it's exact by finding that this is true. And then you can come back here and find your function by plugging in all these values, setting them equal to c, and you'll have a general solution for your exact equation. So let's go through a couple problems. So for this first problem, we can see we have a function. We have a dx and dy and some terms in front, and it does indeed add to 0. So right away, we do know it shows that it's in the form of an exact equation. We need to make sure that it is indeed one by proving that this is true. So we can start by just saying, what is our partial m with respect to y? Well, this term here is our m, so we could say that what is the derivative of y cubed with respect to y? And of course, that just ends up being 3y squared. Then we can look at our n. So our partial n now with respect to x, and it's this term here. So now we have to think, what is derivative of this with respect to x? So we can just treat that y term as a constant along with the 3. So that ends up being just having the x drop out. So we end up with 3y squared. So right here we have proved that it is an exact equation, because 3y squared is the same as the 3y squared we found over here. So now that we've proven that, we can go on and actually find that function, f. So we'll go back and find integral of m dx plus all these terms, and that'll be equal to c. So let's start just with that first term. So that will be that our function f will be equal to this first part of our exact equation. We integrate that with respect to x. And since this is just only has y in here, all we have to do is add an x to the start of that. So we have xy cubed. So now we go back and we're going to start writing out that integral with respect to y. So here we'll have plus the integral, and now it's our n up here, or 3xy squared. And we'll keep going on, and now we'll have the partial derivative with respect to y of what we just found here. So I like to just look at it and say, oh, we'll just write out what we started. So we can kind of take this term and write it after a partial y, and that will be our xy cubed. And then we can close all of this off. We'll just have a dy, and we know that that is equal to a c. So now we can go ahead and simplify this a little more. So taking all these common terms down, we can focus on that partial with respect to y. So we have xy cubed, so we'll just be treating that x as a constant. So we'll bring 3 down, leave it as a y squared, so we end up with 3xy squared. And then closing off everything else. And for this problem, we can see that it actually simplifies down pretty nicely. In the integral, we have a 3xy squared minus another 3xy squared, so we can just cancel those out. And knowing that, we can just come down, and we know that our function f is going to be equal to xy cubed. That will be equal to some function c. So with that, we proved our equation was exact and used that fact to find that our solution is xy cubed is equal to c. So in the second problem, we can see once again we have something that's in the form of an exact equation. We have our first function, our m dx, and then our second function, n dy. So we can go ahead and prove what we need to do, which is take that partial m, partial y. In this case, we have 6xy. That y will go away, leaving just a 6x. And then we have a y cubed, which will become 3y squared. Going on to our partial n with respect to x, looking at this term, it'll end up being our 4y is just like a constant, where there's no x anywhere in this equation, so we can just drop it out. So looking at the next term, we have 3x squared, which will pull the 2 down and get a 6x. And then finally, the last term, we'll subtract off the x will go away, so that will just leave us a 3y squared. Once again, we've proven its exact equation, because these two terms are the same. So now we can go on to finding our function f. So once again, we'll find that f is equal to that first term integrated with respect to x. So we'll take this term down, and we can look at and say 6xy, or y we can leave alone, but the x we can pull a 2 up to the top and leave us with a 3x squared, and then keep that y term. Then the second term is a y cubed. No x is here, so we just put on an x. So minus xy cubed. Then we keep going on. We're going to have a integral. So the first term will be that n we have up here. So writing it all out, 4y plus 3x squared minus 3xy squared. Then we're going to subtract the term we just wrote up here, but we have to do partial with respect to y of that. So if we just think about this term, say we're going to do a partial with respect to y, we can write out that 3x squared y, the y will just drop out, and an xy cubed, the y will come down, leaving us with a squared and a 3. So 3xy squared. And all of that closed off as dy. That'll be equal to our constant c. So once again, we have some simplifications we can do. So in this integral, we have a 3x squared, and we also have a minus 3x squared. We also have a minus 3x squared and a minus 3x squared. So both of those terms will drop out nicely. So what we're left with is just these terms at the front, and then the integral of 4y with respect to y. So we can write that out, and we can have where with the integral of 4y with respect to y is just 2y squared. All of that's equal to c, so that is our final solution. For this exact equation, we showed it's exact. We showed that the solution is 3x squared y minus xy cubed plus 2y squared is equal to c. So with one final problem, we can look and see we have another ordinary differential equation. This time it doesn't quite look the same because we have some function and then some function times our dy dx. So remember that this is a possible way of doing it. We can also think of it as if you multiplied all the terms by dx. So we could just think of this as crossing this out and putting the dx over here. And now this looks more familiar to the form we're used to, where we have this first function is our m, and our second function is our n. So we have to start by proving that these are the same. So our partial m, partial y. And it's a little trickier here. We have our first term. We'll remember that that's just a 0 because it's just the constant. Now the second term, we have two functions of y multiplied by each other. So we have to use the product rule. So we can start by differentiating the first term. That'll just be a 1. And leaving the second term alone, exy. Then we have to add the other way. So we'll leave the first term alone. And then we have to differentiate e to the xy. The y is just like the y is treated like an actual variable, but the x is a constant. So it'll just come down where it's x times e to the xy. So if we do a little bit of simplification here, we can see that we have an exy on both of those terms. So we can just say it's 1 plus xy times e to the xy. So on to the other thing we have to calculate. We have our partial n with respect to x. So once again, we have a function that's just y this time, so that will just be a 0. And we have another function where now, since we're differentiating with respect to x, we have two functions multiplied by each other, so we have to use the product rule again. So we'll just again say that first is 1 when we differentiate, and then the second term we'll leave alone. So going on, we can leave the first term alone, and then pull that y down, because now it's a constant. So we have y e to the x y. So once again, we can simplify again, and we can basically see it's reversed this time. But we can still write it out as 1 plus xy times e to the xy. And right here, we once again have proven these are the same, so it is an exact equation. So now that we've proven that, we can actually find our function f. So first term is our m integrated with respect to y. So that first term got nothing on it, so we can just put an x down. Then plus, we have a y exy, so that y is like a constant, so we can just throw it back up where there is that y already. So we have x plus e to the xy. Then we go on and do our integral. So that first term is just our n, 2y plus x e to the xy. Then we subtract this term here, but differentiated partially with respect to y. So that first term has nothing on it, so that's going to go away. But our second term, we can treat that x like a constant and say it's x e to the xy. So all of that integrated with respect to y. And once again, we have a little bit of a simplification where we see in the integral, we have x e to the xy, and also it's subtracted. So this will simplify a little more, where we'll have x plus e to the xy plus the integral of 2y, which is y squared. We can set that equal to c, and there we have our solution to this exact equation. So as a summary of what we've gone over with exact equations, they are something you can write in the form of m dx plus n dy is equal to 0. Then you need to prove that it's exact by showing that partial of m with respect to y is equal to partial of n with respect to x. Once you've done that, you can find the solution, which is some function f that's equal to the integral of m dx plus the integral with respect to y of your n minus that partial derivative with respect to y of that m dx you just found. And then once you have all of that figured out, that'll be equal to c, and that is your solution. So this has been the Drawing Board by TBPi. Thank you for watching.